Saab began studies for a follow-on to the Saab 35 Draken as early as May 1952, 3 years before its first flight. After an unending series of studies, on September 1961 Saab proposed to the Flygvapnet, Royal Swedish Air Force, the Study 1563, which was to become the Saab 37 Viggen. In parallel, 4 turbofan engines were being considered to power it, and on December 1961 the American Pratt & Whitney JT8D was selected. The firm Svenska Flygmotor obtained a license to produce it locally, on May 1962. This airframe plus engine combination was approved by the Flygvapnet on September 1962. If the background information of this mission is too much for your taste, please note that you can press spacebar at any time to skip most of it. The first of 7 Viggen prototypes flew on February 1967. The test program was long and protracted. The first production aircraft, a JA37, flew only on November 1977. The Viggen entered Swedish service with the F-13 wing on June 1980. The final Viggen was delivered on June 1990, with a total of 329 produced, far less than the 831 units foreseen when the program was launched, but still a lot considering that Sweden was at the time just a small country of 8 million people. Saab was unable to successfully gain export orders for the Viggen. Press spacebar to continue. 4 Viggen variants were initially built. AJ37, attack-jacked, with an attack primary role and interception as a secondary, 108 were built. SF37, dedicated photographic reconnaissance variant, with 7 vertical and oblique cameras on the nose, instead of a radar, 28 units built. SK37, 2-seat training variant, lacking radar and with greatly reduced fuel capacity, only 17 were built, serving with the F-15 wing. SH37, coastal reconnaissance variant, with a longer range attack radar optimized for maritime operation, 27 were built. The development of the much modified JA37 interception variant started on 1968, and its prototype flew for the first time on June 1974. It entered service with the F-13 wing on June 1980, and 149 examples were built. The delays with the Saab 39 Gripen program forced the need for a life extension program for the Viggen, which was ordered on 1991. Starting on 1993, 115 Viggens of the AJ, SF and SH variants were converted to AJS standard, equipped with an improved computer that allowed the use of some weapons designed for the Gripen, like the RBS-15 anti-ship missile, and the BK-90 standoff cluster munitions dispenser. This modernized AJS37 is the Viggen variant that is simulated on DCS by heat blur. Press spacebar to begin. It is a bit dark at this hour. If you can't find a cockpit element, feel free to employ your flashlight, which can be toggled with left Alt+L. Press spacebar to continue. For this training mission, we will cold start the aircraft using a ground power unit. While the Viggen is capable of a completely self-sufficient start using its internal battery alone, having a GPU allows the pilot to perform additional check steps before the engine is started. On the real aircraft, when it is parked on the ground, the flight line mechanic would hook you up to both his own headset and to the air base's wired communications network, Slingon, assuming you're on a Swedish military air base that has that system. To talk to the mechanic you would just talk into the helmet mic. The connection to the mechanic headset works just like a telephone. To transmit on the wired network though, to talk to ATC, your wingman, or whoever else is hooked up to the local loop, then you would need to use the highlighted TRAD push-to-talk transmit button. This system allows tactical communication within the airbase without breaking radio silence. Unfortunately, on DCS this kind of wired communication is not currently simulated. Instead, you have to press the / key to call up the ground crew. Do it now. The DCS communications menu should appear. Its first line indicates that we are employing the interphone. Select F8, ground crew. F2, ground electric power. F1, on.
Chief, turn on the
Press
ground
spacebar
power.
once the crew has connected the GPU.
Copy. Ground power is now on.
Okay, now that the GPU is connected to our aircraft, let's proceed with the cold start procedure. Ejection seat, confirm it is set to safe. The seat is armed, or disarmed, by clicking the handle near the top of the seat. In the handle forward position, the seat is secured and disarmed. On DCS usually the seat is already safe at mission start, but on this training the seat is armed, as the handle being on its stowed position shows. Click the handle to disarm the seat. The real ejection seat is activated by pulling the red ejection handles on each side on the seat. If the seat fails to eject, the yellow backup handles are then pulled. On DCS this action is simulated by pressing left Ctrl plus E 3 times. Seat height can be adjusted with the switch mounted on the left side of the seat, left click to lower it, right click to raise it. On DCS the simulation actually displaces your viewpoint up and down, instead of animating the seat movement. If the seat is not armed, and/or the canopy is not closed, the indicator light HOVO stole illuminates on the right warning panel. Rather than purchasing an existing ejection seat, Saab opted to design their own seat, the Racket Stole FPL-37, which was tested extensively on a Saab Lansen between 1966 and 1969. An improved Mark II version was introduced on 1974, and a 00 Mark III variant was introduced on 1981 and retrofitted to all Viggens. This was the last ejection seat designed by Saab, as the Gripen uses a Martin Baker seat. Press spacebar to continue. Trigger safety bracket, check it is on its safe position. The trigger safety functions both as a mechanical lock on the trigger, as well as an arming switch for the weapons systems. A micro breaker is situated beneath the safety bracket which will activate when the safety is off. This impulse will have different functionality depending on the current weapons mode. Press spacebar to continue. Parking brake, set to on. The wheel brakes can be locked by depressing and holding the brake pedals, then pulling the parking brake handle. The brakes are released by depressing the brake pedals again. Unfortunately, if you employ hardware rudder pedals fitted with two separate toe brake axes, there is a simulation bug that forces you to release them perfectly in sync, or else the parking brake will release. As a workaround, to park the aircraft operate both brake pedals by pressing and holding the W key on your keyboard, instead of using your rudder pedals. The main landing gear is fitted with hydraulic disc brakes, pressure being supplied by the Hydro System 1. When the gear retracts, brake pressure is applied automatically to stop the wheels for stowage. Each main wheel has an anti-skid function, to prevent skids during hard braking on slippery surfaces. If the hydro system fails, the brakes then employ pressure from a hydraulic accumulator, with enough capacity to allow about 20 brake applications. The brake pressure indicator shows the accumulator pressure, which is normally the same as the pressure on the brake system. It is graduated from 0 to 350 kilopons per squared centimeter, its normal operating pressure being 210. The wheel brakes can be individually applied when a smaller turning radius is needed, but asymmetric braking should not be used during thrust reversal, due to the possibility of yaw instability. Press spacebar to continue. Data cartridge, insert into its slot. On the real aircraft, the pilot prepared the upcoming mission on a stationary computer at the airbase, determining the navigation route, waypoints, wind and terrain data, etc. The data generated was recorded on a portable data cartridge, to be carried to the aircraft and uploaded onto the Viggens computer by the crew. On DCS, the mission editor fulfills the role of the airbase flight preparation computer, and the mission data is saved on a simulated data cartridge. Before the cartridge data can be loaded on the Viggens computer, the pilot has to insert the data cartridge onto a transfer slot on the rear left cockpit wall. The simulated action for this insertion is simply to mouse click on the slot, do it now. There are actually several data cartridges available to you, the default being the one with a flight plan created on the DCS mission editor, but there may be also cartridges with auto-generated plans to attack detected enemy groups, or you can even generate one based on marker labels that you place on the F10 map. You can select the cartridge on the ground crew settings page of the kneeboard. Cycle through the available cartridges with left Ctrl plus left Alt plus C. We will learn more about this on a future training mission. Inserting the data cartridge makes it available to the Viggens computer, but you still need to instruct the computer to load the data, which we will do at a later step of the cold start. Press spacebar to continue. Main electric power, Hovedstrom, set to on, till. The Viggens electrical system consists of an AC system and a DC system. The main power supply is an engine-driven AC generator, which also supplies the DC system by means of two electric rectifiers. When using a ground power unit, both AC and DC buses are powered from it, even with the aircraft engine not yet operating. The aircraft DC battery is not used when the GPU is connected. The master warning and the red LT cron lights should have illuminated. On the left warning panel, which is used mostly for engine, fuel, and hydraulic alerts, the following lights will be on. 3 yellow lights, indicating low fuel pressure, bra up, X-tank bra, and tank pump. 3 green lights, indicating that the landing gear struts are extended and locked, no stall, V stall, and H stall. 2 red lights, indicating low hydraulic pressure, Hydra TR2, and Hydra TR1. Plus another red light, indicating low oil pressure, Alljet RIC. On the right warning panel, which is used mostly for alerts by the avionics equipment, the following yellow lights should have illuminated: RHM fell, radar altimeter failure. HUVO stole, ejection seat, and canopy status. MEN BR Reg indicates that the fuel regulator is in manual mode. Sear gas indicates that the oxygen valve is closed. Press spacebar to continue. Low pressure fuel valve, LT cron. Set to on, till. This switch opens the low pressure fuel valve, which allows fuel flow to the engine. The switch also powers up the fuel feeder pumps. When the valve is open, the red light near the switch goes off. Master warning, cancel the alarm. The master warning can be visual only, or both visual and oral. The visual warning consists of 2 red lights on the front panel, that flash alternately whenever a new warning message illuminates on one of the 2 warning panels. The pilot acknowledges the warning by pressing the small black button between the 2 lights. The master warning lights then go out, and the related flashing warning light on the warning panels changes to steady. Cockpit illumination, set as desired. The Vigan internal illumination consists of instrument lights. Each front panel instrument has integral lights, their brightness is adjusted with the highlighted knob. The real aircraft includes an emergency backup for the most important instruments, that is activated automatically if AC supply fails, but on DCS this is not simulated. Panel lights. Both side consoles have integral lighting for its labels and readouts, their brightness is adjusted with the panel bell knob. Flood lights. 3 floodlights, 1 under the left and 2 under the right cockpit combings, illuminate the cockpit side panels. Their brightness is adjusted with the Allman bell knob. There are 2 map lights, 1 on each side of the canopy frame. On the real aircraft, their brightness is controlled with a knob on each light, but this is not simulated on DCS. Press spacebar to continue. Master mode selector, set to its BER position. The CK-37, Central Calculator 37 aircraft computer, is one of the first computers mounted on a combat aircraft. It allowed the Vigan to perform attack missions with just a single crew member, with the computer performing much of the work that a navigator/weapons officer would do on a conventional aircraft, like the Phantom or Buccaneer. The master mode knob instructs the computer which primary operating mode the pilot needs to do. The knob positions are FK, function check, not simulated. BER, Baird SCAP, standby mode, used during aircraft startup, and for data input prior to taxi. NAV, employed during most navigation flying. ANF, used for attack, with most weapon types. SPA, Spaining, meant for reconnaissance functions. Land Ning Nav, navigation landing, used for instrument landing approaches. Land Ning PO, PAR, precision approach radar, optical. Employed for visual approaches and landings. On DCS, the Vigan usually spawns with the knob already on at BER, but on this training it isn't. Please set it to BER. Landing gear lever, down. Confirm the landing gear lever is down, to prevent retraction when the engine start rises the hydraulic pressure. The gear handle has 2 positions, up, on this position the gear is retracted, as well as the canard flaps, which are set to -4 degrees or -7 degrees depending on loadout. Down, the gear is extended, canard flaps extend to 30 degrees. On DCS the thumb lock is not simulated, the handle is toggled by simply clicking on it. Press spacebar to continue. Auto throttle lever, AFK, confirm it is set to off, up. To reduce landing distance and pilot workload, the Vigan is equipped with an automatic throttle system called AFK, Automatic Fart Control. When enabled, the aircraft will automatically control engine thrust between 64% and military power, by moving the throttle lever, and continually adjust it to maintain a given reference airspeed. The AFK is manually engaged by moving the AFK lever down to its AFK position. Its up position disengages the AFK. The AFK can be disengaged also by pressing the AFK quick disengage button on the throttle. The AFK is automatically disengaged when the right main landing gear is compressed at aircraft touchdown. The autothrottle has 3 main modes. Mode 1, when landing gear is up. On this mode the AFK will adjust the thrust to maintain 550 km/h indicated airspeed. It is used prior to landing to maintain a slower cruise airspeed. Mode 2, when landing gear is down, the AFK will adjust thrust to maintain an airspeed corresponding to an angle of attack of 12 degrees, used for landing approach. Mode 3, when the button alpha 15.5 degrees is enabled. On this mode the AFK will adjust thrust to maintain an airspeed corresponding to an angle of attack of 15.5 degrees, used when the shortest landing distance is required. Cycle the autothrottle lever to continue the training, but leave it up. Throttle, set to ground idle. Click the highlighted throttle catch. This action moves the throttle lever to its ground idle position, and also opens the high-pressure fuel valve. Good. This simulates the pilot advancing the throttle to its first catch detent, corresponding to its ground idle position. On the real aircraft, the throttle has 2 catch positions, ground idle, and military power, plus 4 indents, 1 at flight idle, and 3 at each afterburner stage. Since our PC hardware does not have these catches and indents, their effect is simulated with an audible click as the lever is moved past each. The afterburner has 3 distinct zones, 1, 2, and 3. Each zone has a small amount of movement and thrust regulation within it, while still remaining distinct. The chosen afterburner zone is indicated on the right side of the instrument panel. The nozzle indicator shows the position of the engine nozzle, as well as the current afterburner zone, indicated by the numbers 1 to 3. The example figure indicates the engine in afterburner zone 2 and nozzle opened. Press spacebar to continue. Landing light, set to off, middle position. The aircraft is fitted with 3 landing and taxi lights. A 50 watts taxi light is mounted on the nose gear strut. 2 250 watts landing lights are placed on either side of the wheel well on the nose gear. The landing lights are controlled by the highlighted switch. Clicking on the switch will toggle amongst its 3 positions, aft for taxi, center for off, and forward for landing. Sadly, this item is not fully simulated yet, as on both taxi and landing positions only the 50-watt lamp is working. Also, the switch is not textured and is unlabeled. Hopefully heat blur will fix this soon. Press spacebar to continue. Emergency lights, set to off, down. On the real aircraft, the normal instrument panel lighting is AC powered, but if there is an AC power loss, then the emergency lighting would activate automatically, to illuminate the most important instruments. The nod bell switch should activate these emergency lights manually. Unfortunately, the emergency lighting is another feature that is not yet simulated on the DCS Vigan. Press spacebar to continue. Check warning panel lights. Press and hold the warning panel lights test button. The master warning indicator, the alarm sound, and all the lamps on the 2 warning panels should illuminate. Additionally, the following lights are tested via the same button. Low pressure fuel valve warning light, LT cron. Thrust reverser indicator light. Autopilot indicator lights. Stability augmentation, attitude hold, and altitude hold. Auto throttle on, red indicator light, and AFK mode 3 white indicator light, alpha 15.5 degrees. Thrust reverser, reduced transonic indicator light. Stores released indicator light, fall blast, not simulated yet. Afterburner 1, 2, 3, indicator lights. This is the last item, you can release the button now. When you release the test button, on the warning panels, those lights that have a small white square next to them, should remain lit. Unfortunately, on DCS this is not modeled correctly. Press spacebar to continue. Generator, set to on, till. For the Vigan, its main electric power source is the main generator, which is driven by the engine and will provide AC power during the flight. Additionally, there are 2 parallel rectifiers that will provide DC power by converting AC from the generator. On loss of power from the generator due to a failure, the backup generator is brought online. The backup generator consists of a small ram air turbine, RAT, mounted on the left side of the fuselage, which deploys automatically upon an in-flight AC failure. The RAT is effective at speeds of 300 to 700 km per hour, speeds over that may lead to damage of the RAT, and at speeds below no power will be generated. The RAT is on a deployed status while the aircraft is on the ground, and is retracted automatically on gear retraction, but is not connected as a power source unless required. Set the generator switch to its left position, to have it connect to the AC bus as soon as the engine attains enough RPM. Autopilot yaw correction, set to 0. The autopilot makes automatic trimming in yaw, using a signal from the yaw accelerometer. Should the aircraft fly unbalanced during automatic trimming, it could be caused by an unbalance in the yaw accelerometer. This unbalance can be trimmed out by employing this knob. Press spacebar to continue. FR-24 radio. Set to normal plus guard. The Viggen is equipped with 2 radios. The FR-24 is the secondary or backup radio. It can only operate on VHF AM and has a power of only 3 watts. It has 3 fixed channels, E, F, and G, plus the emergency guard channel, at 121.5 MHz. It does not have manual tuning capability. It is powered by the main battery, so it can be used without need of ground power. Its mode selector controls both the main and the secondary radio. To use the main FR-22 radio, this selector must be at either of the 2 norm positions. Norm plus L-arm, normal FR-22 main radio functionality, plus monitoring of the guard frequency. Norm, normal FR-22 main radio functionality, with no guard monitoring. To employ the FR-24 radio, you would select one of these positions. H, guard frequency monitoring, using the FR-24 backup radio. E, F, and G, preset channels defined on the mission editor. We will not be using this backup radio today, so set its mode to norm plus L-arm, to set the FR-22 as main radio. Flight recorder, mic bank, set as desired. On the real aircraft, it is used to record all voice radio communications, but on DCS it is not simulated. Press spacebar to continue. Radar brightness, AJS radar, set to its middle position. It has no effect at the moment, because the radar is automatically turned off when the aircraft is on the ground. Press spacebar to continue. Radar panel, set initial radar settings. The PS-37A is a ground mapping radar designed for targeting ships and, in a lesser capacity, aircraft. It can be used against ground targets, however its effectiveness highly depends on the contrast with the surrounding area and the target size. The radar is also used as a navigational aid, and is very closely integrated with the navigation suite. The radar does not lock a target as can be seen on other radar types, but serves to identify the position of terrain features and potential targets. In addition to the search mode, the radar will operate in a ranging mode during certain ground attack and in the air-to-air modes, in order to increase accuracy of the sighting mechanism. Radar mode selector, set to its A0 position, radar off. It's a 3-position switch, on top of the radar control stick. A0, switch forward, radar off. A1, switch in middle position, radar on, wide search mode, with plan polar indication, PPI, representation. A2, switch aft, radar on, narrow search, B-scope representation. Press spacebar to continue. Anti-jamming, AS, filter mode selector, turn knob to position 1. Toggles anti-jamming filters. With the filters, it might become possible to determine the distance to a jamming target, and then perform a successful target fix. Passive search, passive spaining. Set to off, FRAN. When in passive mode, the radar will receive active jamming signals and display the direction from where they are received, but will not emit anything itself. This is useful when trying to estimate the location of ships equipped with jamming devices without triggering enemy radar warning receivers with your own radar. Press spacebar to continue. Radar processing mode switch, LIN, log. Set to log. The logarithmic display mode is the default mode, where the terrain contacts are more nuanced and different terrain types can be discerned. This gives you a better depiction of terrain elevation variations. The linear display mode is the high contrast mode where the difference between terrain types and elevations are not as important, such as during terrain avoidance or in air-to-air modes. Radar antenna elevation dial set to its middle position. The radar is, in most cases, automatically steered by the AJS37 flight computer. However, the antenna elevation can, during the normal search mode, be adjusted ±10 degrees from the set angle by use of the antenna elevation potentiometer on the radar control stick. On the real aircraft, this knob has a detent on its center position. On the sim, unfortunately, there is no way to see what the current elevation is. Press spacebar to continue. Land Sea radar altimeter mode, set to correct position depending on the mission. The radar altimeter detects the current altitude above ground in the interval of 0 to 600 meters. The radar altimeter is normally always activated, but it can be turned off with the RHM switch on the navigation panel. This switch changes the signal modulation of the Doppler radar lobes to match the surface type over which the aircraft is flying, either land or sea. For this mission, set it to land and press spacebar. Thrust reverser handle, confirm it is off. The thrust reverser is used on landing, directing the engine thrust forward to significantly shorten the landing distance. The reverser claps close the rear exhaust, and instead direct the exhaust jet forwards and slightly downwards, through 3 slits in the jet pipe assembly. The reversal system is engaged by pulling the reverser handle REV on the left side of the front panel. Pulling the handle while airborne will pre-select reversal. Do not operate the handle while the engine is off, or the red reverse thrust reduction transonic alert will illuminate. Press spacebar to continue. Attitude Director Indicator, ADI, FLI-37. Check proper alignment, fast direct if needed. The ADI is the main indicator of the aircraft orientation. It consists of a 3-axis sphere which indicates pitch and roll angles, as well as heading. The ADI also has a vertical speed indicator, VSI, a side slit ball, and flight director needles. The flight director needles are used only during landings, and are normally slaved to the HUD, showing commanded altitude and heading. The needles are stowed during takeoff and visual landing modes. The FLI-37 ADI automatically fast directs on startup. The initial course setting, manual or during takeoff, will further refine the displayed course. The fast direct can be repeated in case of an error or failure. This is done by pressing a button at the bottom of the radar screen. Fast direct should be done in acceleration-free flight to avoid errors during alignment. Click the fast direct button to continue with the mission. FR-22 radio, set correct base and channel. The Viggen's primary radio, the FR-22, is a combined VHF-UHF radio, which can be manually tuned, or employ one of 844 preset channels. On the simulator, only 42 presets are actually implemented, due to DCS limitations. The real FR-22 is AC powered and needs ground power to be used, however, on DCS it can work with just battery power. To learn which the preset for Creech Airbase is, press right Shift plus K to open the kneeboard, then page forward until the Airbases page, which lists the radio frequencies of every airbase on the map. Use right Shift plus page up or page down to browse the full Airbases list. To select the proper preset, first turn the base selector dial until its base indicator display shows the desired airbase identification number. For Creech its number is 01. Unfortunately, the radio visors are not backed up. Use the flashlight, left Alt plus L, if needed. Next, press the corresponding base selector button. For example, press AG to communicate using Creech's UHF frequency, or press B to use Creech's VHF, etc. Once you have selected the appropriate preset, press right Shift plus K again to close the kneeboard. Just to check that the radio is properly tuned, we will contact ATC to request startup clearance. Press the key or button that you have binded to the FR-22 push-to-talk, on my case it's right Control plus P. The DCS communications menu should appear. Select F5, ATC. F1, Creech. F3, request startup. Press spacebar once air traffic control gives you clearance to start, and press F12 to exit from the communications menu. HUD reflector glass, set to its landing setting, lower. The Viggen was fitted with one of the first digital heads-up display ever fitted to a jet fighter. It provides the pilot with visual references to aircraft attitude, flight information, and aiming cues for most of the weapons. The HUD is based on a cathode tube being reflected via a series of lenses onto a glass panel. The glass frame has a higher and a lower position, to allow the displayed symbology to be visible even during flight at high angles of attack, such as during takeoff and landing. The HUD position, raised or lowered, is operated by a lever on the left side of the HUD base. Set the reflector glass to the lower setting, to allow display of takeoff and landing modes. Press spacebar to continue. HUD slave switch, Slav SI. Check it set to off, F. For very low-level flight, under 100 meters, this switch enables a decluttered HUD mode. Only the attitude reference line and flight path vector remain shown. The heading tape can still be displayed by pressing the reference button on the control stick. Altimeter source selector, HUD CISI. Set to LD, barometric. The altimeter source used by the Viggen computer can be toggled with this switch. The LD position uses barometric altitude, while RHM uses the radar altimeter as source. Backup artificial horizon, uncage. Indicates aircraft orientation in pitch and roll by rotating a cylinder against a fixed symbol. Pitch is marked every 10 degrees. Roll is indicated by the moving index on the bottom. Click and hold its button until its fixed reference is aligned with the horizon. Press spacebar to continue. Backup altimeter. Set to QFE value, atmospheric pressure at the airport. The backup instruments are operated from the pitot mounted on the tail fin, and thereby are separate from the main instruments and the flight data unit. The backup altimeter indicates current barometric altitude. 2 needles, one graduated for hundreds of meters, and one for thousands. Rotate the knob until the altitude reads 0. Note that 0 is at the 6 o'clock position of the gauge. Press spacebar once set. Main altimeter, set to QFE, atmospheric pressure at the airport. Indicates barometric altitude in meters. The pressure is expressed in hectopascal. Rotate the pressure setting knob by right-click and drag, or using the mouse wheel, to change the pressure setting. Pull the knob by left-clicking on it to set a standard QNE pressure of 1013.25 hectopascal, indicated by a STD flag covering the pressure indicator. Pushing the knob in with a left click will return to the normal adjustable pressure. Rotate the knob until the altitude reads 0. Press spacebar once set. Engine pressure ratio, check. This gauge indicates the ratio between the total exhaust pressure and total intake pressure of the engine, EPR. The indication ranges from 1.0 to 2.7, scale graded at 0.5. Can be used to roughly indicate amount of thrust produced by the engine. It should be around 1.0. Press spacebar once set. Fuel indicator, check. Its main needle indicates the remaining fuel volume in percentage. Should deviate a maximum of ±5% from either 106 or 131%, full fuel load without, or with, an external tank. The striped needles indicate the currently needed amount of fuel to fulfill the planned flight as programmed into the computer. The required fuel is continuously calculated and displayed, as the amount of fuel required from the aircraft's current position to the next destination, and the remaining route to the primary landing site, L1, plus the amount of fuel required for a landing. The computer accounts for the increased drag, due to weapons and planned flight path and profile, taking into consideration the variables of ingress speeds and wind. In addition, a preset fuel reserve is added to this calculation. This preset amount can be set by the pilot to ensure a greater margin. Press spacebar to continue. KB countermeasures pod and APP-27 radar warning receiver. Set as desired. The APP-27 RWR system alerts the pilot of being illuminated or locked on by a radar threat. The RWR sensors are fitted on the leading edge of both main wings, plus a rear sensor mounted on the boom above the jet exhaust. We will study this whole subject in more detail on a dedicated training mission. For now, just set the RWR knob as needed. Off, Fran, RWR is off and will not provide any warnings. Lights, LJUS, visual warning only, audio warnings muted. Lights and audio, LJUS and LJUD, the RWR emits both visual and audio warnings. For this mission, set it to lights only. The Viggen didn't include any built-in countermeasures on its original design. After the Vietnam and Yom Kippur Wars demonstrated the need, an external pod was designed for the Viggen. The KB pod contains both chaff and flares in separate sections of the pod. Since the pod can only be mounted on the inner wing pylons, the aircraft likely has to sacrifice some offensive weaponry in order to provide countermeasures capabilities. The pod can be carried on either wing, or both at the same time. It contains 36 flares, plus a large amount of chaff. The pod cannot be jettisoned. Press spacebar to continue. Exterior lighting, set as desired. The navigation lights are mounted on the leading edge of each wing, red and green, plus 2 white lights mounted on the tailpipe assembly. They are controlled by the switch lantern, as follows. Neutral, middle, navigation lights off. Hell, navigation lights at full intensity. Have, navigation lights at half intensity, except rear white lights, which remain at full. Set to hell position. Small white position lights are placed on the back of the wingtips and the outer elevon servos, as well as inside the air brakes, to indicate when opening air brakes during formation flight at night. The position lights are controlled by the LED LJUS switch, and their brightness by the formation position lights brightness dial form LJUS, LED LJUS. Set to on, till. The formation lights are mounted on the side of the fuselage to aid in formation keeping at night. Additionally, a light is placed on top of either wing to illuminate the tail number on the vertical stabilizer. The position lights are controlled by the form LJUS switch, set to on, till. 2 anti-collision beacon lights are mounted on the top and bottom of the fuselage. They are controlled by the switch anti-COLJUS, set it to on, till. IFF system. Set as desired. The identification friend-foe system is not currently simulated on DCS. Press spacebar to skip this step. Course correction, course core, check and set. Click on the magnetic declination cover and set the magnetic declination knob according to the world region you are flying. The correction values for the year 2016 are 7.2 degrees for Caucasus, 14.2 degrees for Nevada, 2.1 degrees for Persian Gulf, 0.8 degrees for Marianas, 4.9 degrees for Syria, and 15 degrees, west of the map, to 2.2 degrees, east, for South Atlantic. Please note that these values are for the correction. The actual magnetic declination is the negative of those values. The knob limits are plus/minus 10 degrees, so for Nevada and South Atlantic, it is not possible to achieve full correction. DCS will automatically set the knob appropriately at mission start. Also, on the Viggen's kneeboard you can find the current magnetic deviation for this mission. Press spacebar to continue. Windshield anti-ice, Warmluftspolning von Trutte, set to off. The effect of this knob is not simulated on DCS. Press spacebar to skip this step. TILS channel selector, set to A, automatic. TILS, Tactical Instrument Landing System, is the instrument landing system for the Swedish Air Force, introduced with the System 37 Viggen. It is designed to allow instrument landings in poor weather. The Airbases page of the kneeboard shows which TILS channel each airbase employs. When the selector is set to automatic, the computer will attempt to use the channel pre-stored in its memory. You can select it manually in the event of a computer failure. Press spacebar to continue. Radar altimeter, confirm it is on, till. The radar altimeter is used to determine the current altitude above ground in the interval of 0 to 600 meters, and at roll pitch angles lower than 40 degrees. The system consists of a transmitter unit in the left fuselage bay and 2 receivers on the bottom of the fuselage. The radar altimeter is normally always activated, but the computer turns it off automatically when the aircraft is on the ground, except for the control check. This switch lets the pilot power the radar altimeter, on or off, manually. Press spacebar to continue. Weapon selector, set as needed for the mission. Rather than selecting a weapon pylon, like other aircrafts, on the Viggen this selector designates a weapon type. Each position of the knob may be used to select multiple types of weapons. However, loadout limitations prohibits the carriage of different weapons, which would need the same position of the knob. The weapons selector has 6 positions. SJO plan selects RB-05 missiles for anti-shipping or bombs for level release. RB-75 Mark DYK selects RB-75 or RB-05 missiles for air-to-ground or bombs for dive release. Luft-RR selects RB-05 for air-to-air or bombs for radar release. Aachen-Jagd 4 gun pods in air-to-air mode. Attack selects most of the air-to-ground weapon types. IRRB selects Sidewinder missiles. For this mission, set the knob to IRRB. For the Sidewinder missiles, you can use the highlighted knob to adjust the volume of its heat seeker audio tone. Turn it full down, as it can be a bit annoying. Weapon release mode, set as needed for the mission. This switch is used for 2 kinds of weapons. For the RB-04 or RB-15 missiles, sets either Siri, multiple, or impulse, single, release. For rockets, sets either normal mode, norm, or long range mode, LA. It does not apply to our current weapons, so press spacebar to continue. Weapon targeting mode, set as needed for the mission. This switch is used with 3 weapons. For the RB-04, sets either Malval, single, or prep, group, ship targets. For the RB-15 and BK-90, selects between standard predefined attack settings or custom values entered on the computer. It does not apply to our current weapons, so press spacebar to continue. Circuit breakers, right CB panel. Confirm all on, pushed in. While most circuit breakers of the aircraft are actually meant for the maintenance crew, stored away on the various electric bays of the Viggen, the pilot does have access to a small circuit breakers panel on the cockpit right sidewall. The figure shows what equipment is controlled by each of the pilot's circuit breakers. While they are animated and can be pulled out and pushed in, their effect is not currently being simulated. Press spacebar to continue. Data input. Load the data cartridge onto the computer. Visually confirm that the data cartridge is inserted on the data cartridge slot. The data cartridge can only be loaded when the aircraft is on the ground, and loading the cartridge will automatically clear all previously entered mission data. Press spacebar to continue. To load the flight plan data from the cartridge, first turn the computer data selector knob to its Ref Lola position. Ref Lola means reference number or longitude-latitude. It is the computer mode used for navigation, where geographic coordinates are designated either as a longitude-latitude, or by reference number, for example an airbase known to the computer. Next, set the input-output data switch to in, as we will be entering a value. Good, now enter the code 9099, using the computer keypad. Okay, the visor is showing 9099 and 00 for the last 2 digits. During the data transfer process, the leading 9 will blink. A failed transfer would be indicated by the first digit no longer blinking, but the display still showing 909900. Now, press the LSSKU button to start the data transfer process. Good, the transfer was successful, indicated by the visor changing to all zeros. Now set the input-output data switch back to UT, out. Set the data selector knob back to Act Pause, active position. On this mode the visor displays our current position, the turn-nav status, and the estimated navigation error. We will study the computer functions in more depth on a future training mission. Press spacebar to continue. Oxygen. Check pressure and open flow valve. The gauge indicates the remaining pressure in the aircraft oxygen bottle. A valve mounted next to the indicator regulates oxygen flow. Its upper position, till, opens the oxygen flow. Do it now. Indicator system test. The indicator system test button, control, is used to test the altitude warning light, as well as the following systems. Fire warning, fuel indicator, High angle of attack warning, landing gear indicator, and radar altimeter. Press and hold the control button. Check the following. High alpha warning sound, the flight stick vibrates slightly. Fire warning lights illuminate, 2 brand red alerts on the left warning panel, and a single brand GTS on the right warning panel. Landing gear green lights, land stall, should go out. Not simulated yet. The low altitude red warning light, at the corner of the radar display, illuminates steady. The fuel indicator shows a test value of 29 plus minus 3% of fuel. The computer's visor shows a leading 1, plus the current CK program version number, 0990. The green FK light should go on, but it is not simulated yet. You may now release the control button. Good test. Press spacebar to continue. Canopy, close and check locked, may be closed earlier if needed. The canopy is operated by the canopy actuator handle. The handle is pushed forward to close, and backward to open. The middle position is neutral. The cabin is sealed automatically if the canopy is closed and the engine is on. If the canopy is opened or not locked, the indicator light of STOL is lit on the right warning panel. The engine is started by a gas turbine starter unit, GTS. Essentially a small jet engine, it runs on the main fuel source. Once it reaches the correct RPM, the GTS clutches onto the engine and accelerates it until it reaches self-sustaining RPM. The GTS is itself started by a small electrical motor, which accelerates the GTS unit to its lowest sustainable RPM. The aircraft can be started either via the battery or by use of the ground power unit. The battery can sustain about 3 startup attempts before being drained. The GTS does not provide any electric power on its own, and can only be started via the automatic startup sequence. The whole sequence is initiated via the start switch, or automatically in case of an in-flight start below a certain engine RPM, where the GTS is necessary. Engine start switch, set to on, till. On the real aircraft, the switch must be manually held at on for 2 seconds, before it is magnetically held by the starter, but this is not yet simulated on DCS. The engine start sequence is electrically controlled and operates automatically after pushing the start switch. The start sys caution illuminates when the GTS initiates its power-up, which takes a few seconds, then it will clutch to the jet engine, indicated by its RPM increase. At around 10% RPM, fuel enters the engine and the igniters are energized. The tan sys caution will illuminate at this point. The generator is now online. The red ELFL alert goes out. At this point the start switch goes off, the GTS is stopped, and the start sys and tan sys cautions will go out. The engine has reached ground idle. Check the following items: RPM, between 55 and 65%. Idle exhaust gas temperature, EGT, not more than 350 degrees Celsius. Engine pressure ratio, should stabilize around 1.0. Engine nozzle position should be fully open. SPAC stabilization, should have turned on automatically. Check its green light is illuminated. Warning panel lights. All lights should be out, except the following: OL jet rick. The oil pressure caution can be lit for a maximum of 60 seconds. X-tank bra, the drop tank fuel pressure illuminates, for as long as the engine RPM is below 70%, as the bleed air being produced is not enough. The 3 green stall lights for the landing gear will remain lit until takeoff. This completes the ground idle checks. Press spacebar to continue. With the engine now running, we will ask for the ground power unit to be disconnected. Press the / key to call up the ground crew. The DCS communications menu should appear. Select F11, parent menu. F8, ground crew. F2, ground electric power. F2, off.
Chief, turn
Press
off the ground
spacebar
power.
once the crew has disconnected the GPU.
Copy. Ground power is now off.
The next few check steps should be performed irrespective if the start was done with or without ground power. Roll trim, check and center. The Vigan elevons lack conventional trim tabs, so trimming in pitch and roll operates by moving the neutral position of the control stick. The trim is operated by the pilot using a small hat switch on the control stick. There is no indicator on the simulated cockpit to actually check the amount of roll trim applied, but you still can check it using the simulator's controls overlay, which you can toggle with the keys right control plus enter. Use the flight stick trim hat to input a bit of trim, both on pitch and on roll, so that you can see its effect on the controls overlay. Note how the neutral position of the simulated flight stick moves within the simulated cockpit. Press spacebar to continue once you have applied trim. Press and hold the highlighted roll center button. The simulated flight stick should move towards its center position in its roll axis. Note that any pitch trim is not affected, only roll. Press spacebar once the roll trim is centered. Yaw trim, check and center. On the real aircraft, yaw trim is achieved by an electrical trim actuator within the fin. This actuator transfers trim